Hello, everyone. Welcome to the fourth webinar in the joint Tran-SET webinar series, which will cover a variety of research projects related to innovative technology, techniques, and processes in transportation infrastructure inspection. My name is Chris Melson. I'm the program manager of Tran-SET, which is Region 6's University Transportation Center, Region 6's UTC. The webinar is jointly hosted by Tran-SET, by our research center, but also by Region 2's UTC, which is the Center for Advanced Infrastructure and Transportation that is led by Rutgers University. I do ask the attendees, if they are interested in our research, please feel free to visit our website. We do have quarterly newsletters. Obviously, these webinars. We also have a mail listserv. So if you are interested in joining the mail listserv, please visit our website. So today we'll have 4 20-minute presentations, and we'll save the questions until the end of the 4 presentations for a quick group Q&A. So without further ado, I will introduce our first speaker, Dr. Fernando Moreu. Dr. Moreu is an assistant professor in structural engineering at the Department of Civil, Construction, and Environmental Engineering at the University of New Mexico. He also has concurrent appointments in the Departments of Electrical and Computer Engineering and the Department of Mechanical Engineering. He's the founder and director of the Smart Management of Infrastructure Laboratory, SMI Lab. His industry experience includes working for ESCA consultants for over 10 years, with experience in the design, construction, and replacement of over 30 bridges in the U.S. His research interests include structural dynamics, structural health monitoring, wireless smart sensor networks, augmented reality, unmanned aerial systems, human-machine interfaces, and aerospace structural design, monitoring, and reusability.
So yeah, thank you, Chris. It's great to be presenting the first on this list of presenters today, and I have a introductory, very nice introduction by Chris. I will be talking today about development, training, education, and implementation of low-cost sensing technologies for bridge structural health monitoring, and I will be talking about new technologies that we did with Tran-SET, focusing in sensors, technologies, drones, and we'll see how those get implemented. First of all, the work that I have here is basically done by the students and visiting scholars. They are a mix of electrical engineering, computer science, mechanical engineering, and of course, civil engineering, and all their work will be presented today. This is here at the University of New Mexico on Monday, actually. The contents of my presentation, I will start with a brief motivation. I will talk about the interest on remote sensing. I have some of the projects that we did involve the other technologies and the outreach and training, which was very important on this proposal. This is the American Society of Civil Engineers Civil Engineering report card. You can see they give a grade to the infrastructure that you receive, and if you give these grades when you go home to your mom, she won't be too happy. You can see very low letters, and in particular, the average from the last report card 2017, it was D+. So we need to do a little better than this, and from that approach, we're thinking that the main decision comes from the inspection. I mean, I worked 10 years in industry, so that was the motivation of thinking about how these inspectors are collecting this information to prioritize. That's one of the core interests from Tran-SET, how to maintain, prioritize decisions from the built infrastructure out there. We can see that, and this is in the top of the list, but humans have difficulties collecting objective information on the field because humans are humans. So we're thinking, okay, what is the future telling us to do? This is from the American Society of Civil Engineers. Well, the society tells us that the civil engineer of the future will be reliant on and leveraging real-time access to living databases, sensors, and diagnostic tools to make decisions. So we think if the society is telling us where to go, universities should also go in this direction. So I'm going to be talking about this data, this collection with technologies, and how these humans can understand and be more familiar with using these technologies. The University of New Mexico is unique not only for our national lab environment, it's a research one university, we prioritize research, and also we have a population of 67% from underrepresented groups. That's very high and very unique on the country. So one of the motivations on Tran-SET was how can we reach to these minority underrepresented groups, female, from early start. There is an interest of attracting this first generation of students to low cost, ready to use technologies to train the engineer of the future. On the same time, we try to make this technology accessible to the workforce. So in today's introduction of technology for inspections, we can see that we are doing better than before. We're bringing technology on the field, but we think this interface of data with humans, we can increase, reduce the cost, increase the accessibility to this data, maybe explore this interface of the users and the data that is collected. And that's where the sensors become as gatekeepers of that interface. It's very important to collect these inspections to prioritize repairs, but we need to collect the information that is valuable for the owner. So I've been prioritizing on this presentation the importance of collecting displacements from railroad bridges, because they couldn't do much with accelerations. They couldn't do much with large amounts of gigabytes. They don't like gigabytes. They don't like modal shapes. So they wanted to tell how much the bridge is moving. So I typically stress, let's ask the owner for what they need, and we'll provide them what they want. This is a bridge monitoring on Chicago. This is using sensors attached to the rail. When the train is crossing, you can see the first two wheels, the first four wheels from the first car are very high from the locomotive. The next ones are microstrains that are a little less, because the cars it's an Amtrak car at 80 miles an hour. So you can see how sensors can tell you interesting information of the environments that you're trying to explore. So that's what we're looking for. How can we collect this data with these sensors that can inform about the usage of the infrastructure? So from the data on the field and the collection of displacement, we found out that bridges in worse condition on this table from the left to the right, you can see these columns are 27 measurements under trains, and each group of bars are different bridges. So you can see red is about 40 millimeters on the vertical direction. Red is not good. Moving 40 millimeters is a concern. So we're trying to say, hey, if we could collect these displacements with very low cost technology, all the inspectors could attach their sensor, wait for the train, look how much is moving, and decide if it's needed to slow the train, or the opposite is true. If you think it's moving a lot, the sensor tells you it's moving not as much, maybe under your 3/8 of an inch, 1/4 of an inch, 5 millimeters, then you don't need to worry. Objective measurement is of value for the determining these thresholds. We've been using a low-cost approach that is actually a convergence between low-cost technology and accuracy that we need on the field. And we call it low-cost efficient wireless intelligence sensors, LUWIS. When we published this paper on the Mechanical Systems and Signal Processing Journal, it was the passing away of the actor, Jerry Lewis. So we decided to name our sensor on his honor. So I'll be talking about LUWIS at this low-cost efficient wireless intelligence sensor on the presentation. It's based on a microcontroller from Arduino, very well known by the community. We use a low-cost accelerometer that can collect triaxial accelerations for only $4 to $8, XYZ. We get 14-bit, up to 8 Gs, 800 sampling rate, very linear. We have wireless XB antennas, and we can have this wireless collection for about $43 to $73, depending on the range of sensors that you want to build. If you build 10 sensors, the price is on the higher range. If it's a higher number, 1,000 sensors, it can come down. And we actually designed it to measure outdoors. I can show you how this resists rain or snow, or you could have your concern about the battery. We have solar panels that can allow you to collect continuous data, and you don't need to rely on the power cord. And we have it certified. So we wanted to see if this wireless sensor can measure the accuracy of the displacements that we needed. So we conduct experiments on the laboratory first, replicating this displacement. This is the sensor on the left. You can see the antenna on on the table. This is a shake table moving horizontally, right to left on your screen. You can see how the acceleration is validated with a commercial accelerometer. And then on the right-hand side, you have the LVDT. This is the setup, and we wanted to measure if the trains that you were seeing crossing could be also collected on the field by this low-cost sensor. So I'm going to show a real train crossing event where we actually measure this acceleration, and we convert it in displacement because we cannot bring a displacement sensor on the field. We need to double integrate with an algorithm that we develop and compare if the real-time LVDT displacement can be estimated by our low-cost Lewis sensor. So this is the real bridge. This is the acceleration on the top, displacement on the bottom. You can see that transverse displacement. And this is our experiment on the laboratory. It's an upside-down bridge, and imagine we are running the trains on the table, okay? So it's moving right and left, and we have our wireless sensor on the table like if it was the top of the bridge moving. Here you can see the results for up to 8 train crossings at different speeds and different directions. And we compare the reference, which is the true displacement. We compare the commercial accelerometer on red and the Lewis acceleration. The time domain demonstrates that the estimation is as good as the commercial and as good as the reference for the time domain. Also, we wanted to have a comparison on errors. Under 15, 20%, the railroad is happy with this estimation. So even if you have the commercial sensor on blue or the Lewis sensor on yellow, they are comparable. And we also conducted on the next slide the frequency domain comparison for the 4 trains on the southbound on the left, the 4 trains on the northbound on the right, and blue, or red, and yellow also coincide. In conclusion, we can have displacement that the owners can collect on the field without any reference wirelessly, and they can use these measurements to inform decisions. We also, on this Tran-SET project, wanted to bring other technologies, and one that has been very attractive is how can we use drones to collect information of interest. So we've been interested to bring this displacement on the drone. When you collect a video of entire bridge, it's a lot of data. You would like to know how much is moving. So that's why we attach this laser. Imagine we cannot attach our sensor. How could we measure this displacement? We would just fly with our drone perpendicular to the bridge and see with our laser on the right-hand side if we can measure the target moving under trains. And we did this on the field. And I have a little video that I hope you can see on the next slide. We did this in Albuquerque on the University of New Mexico on the southwest of campus on a balloon fiesta where every year we have up to 800 balloons. So it's certified for doing this kind of flights. It's about a minute and a half. As it's very loud, please can tell me to go over the volume here. So we did 3 experiments shooting the laser to our suggested flight. And as you can see on there, I'm moving the board like if it was a bridge, and you can see how I have the laser on the bridge and the LVDT with the validation on the other side. As you can see, the laser is also getting outside of the board. We thought that was a concern. The results show that that is not an issue, even though the drone may be hovering outside of your reflective tape. That's not a problem as long as your surface is flat, which was our assumption. We only flew about 5 feet from the ground because that was our validation purpose. And as you can see, the tether from the drone is connected to our data acquisition system. On the future, that would be also untethered. But again, we wanted to validate the ability of a laser collecting real-time displacement on your bridge. It was actually in collaboration with the National Academy of Science, the CN Railroad, so they provided feedback, the Los Alamos National Lab, the American Association of Railroads. So they provided very practical feedback about if this technology could be of use for them to see. We moved the drone a little farther away for 7 minutes, about 21 feet, and we also collected about 30 seconds, 40 seconds of displacement on that bridge. So the idea is to validate if the laser on the drone without the reference on the field can collect the same accuracy that you get with your LVDT, your reference on the fixed point. This was a successful landing, and we were very happy with the experiment, as you can see. The student really celebrated that we concluded successfully. This is the data of 3 of the experiments, and as you can see on blue and red, they are very close. We collected some comparison and also saw that we can collect the peak-to-peak similarly with the LVDT, which is the accepted reference point, or the laser, which was, in conclusion, a good match in phase and amplitude for these experiments. Toward the end of my presentation, I see I have another 5 minutes here. I have an overlay of this exploration of technologies that we did on this year 1 of Tran-SET. As I mentioned, humans are interested in cognition and decisions based on their rounded shape, as you can see the brain on the top left. And structures are square and 90-degree angles. So we want to break this intersection about time and space with the inspection routines and also the visualization of these inspections. So we are interested in the human perception of data, and we are measuring how humans actually feel data. So we've been using electroencephalograms and collecting how inspectors observe, in this case was with different languages, and collect these different parts of the brain where you actually get surprised or get familiarized with a change. So we are using that for inspecting the structures. It's a new area for structures, not so new for psychology. We've been exploring augmented reality. In fact, on the next Tran-SET webinar, I'll be presenting a topic. It's been very successful. We are looking forward to doing more on this inspection, and I believe the next speaker will be covering how this can be used. In our case, we have an interest for a change detection. So that was also done on year 1, where we wanted to inspect a bridge very quickly. As you can see, this is a sign, overhead must turn, but the track couldn't turn. The tracks continue impacting on these bridges and breaking the infrastructure, and also there are some concerns about casualties and injuries on those impacts. So we wanted to see, can we protect the bridge with a beam and can actually inspect the bridge on real time? So we created a change detector. We can overlay these impacts. We tested in the Chinese Earthquake Administration collaboration. We created a bumper, and I have a little video here that you can see how we created this impact. So there is an impact on the bridge on the side, and we collected this high-speed video of the impact. You can see it's coming up on the webinar, how you impact laterally, and you have some damage on the bridge that you want to quickly assess with a change detector. So we have that conducted with a 3D cloud using the HoloLens from Microsoft, and we compare if we need to replace or not. So we collected this 3D cloud, save it with the time machine, and compare before impact and after impact. As you can see on the screen, we have the green to be before, the gray to be after the impact. I'll be covering some of this on September. We've been also installing this Lewis sensor in other structures such as rockets. So I have higher interest from students to put sensors on rockets than on bridges. So that's been attracting this new generation of engineers to using technologies for structural performance, because the idea was to engage the future users of technology. We identified on the process that the sensor that we did for bridges can also be used for rockets, and that was in collaboration actually with the Albuquerque Rocket Society. There's some interest from reusability on rockets from NASA. We had a small project that we also encouraged the collaboration with Tran-SET, and that was very successful. So we wanted to include that on the outcomes of this student engagement, where, as you see, they program their application, they have the wireless connection of the rocket, and they launch the rocket. So you see how that comes up. That is the trajectory of our sensor that was inside the rocket. So it was very, very interesting for understanding the performance. And in summary, I have a lot of positive feedback. I have 1 more minute here where the students, this is an activity with high schoolers in the Summer Transportation Institute here at the University of New Mexico. The students get to build their sensors the morning and get to put them later on an infrastructure the same day. So as you can see, a lot of interest for the students in actually touching sensors, connecting wires. My PhD students and graduate students have done a tremendous work in mentoring them. As you can see, they are, this is in the classroom in the morning. They are, every 2 students receive 1 mentor, so that's why they get encouraged on this exposure to smart transportation sensing. Again, they did this in the morning, an hour, 2 hours. We go later to the tramway and they install the sensors that they built to understand the performance of that tramway. So you can see, we also use it for graduate students. If high schoolers can do it, graduate students can do it too. For dynamics class, first time that we did this in a civil engineering homework. As you can see, they did the same. If the high schoolers can do it, the graduate students can do it. Very successful. We also teach industry about local sensors. We did the International Modal Analysis Conference. Engineers typically don't have this hands-on experience, so we also teach them how to build LUIS. Very, very interesting. And at the end of our year 1, we conducted a workshop to get feedback on the ranking from the industry, and their opinion has been very useful to actually develop technologies that they can use. These are my conclusions. Thank you for your attention. We're talking about using sensors to prioritize inspections. I learned that from industry for 10 years, and everything that breaks this human infrastructure interface with technology will be of interest for the engineers of the future. I will be looking forward for the Q&A session. Thank you. Chris, back to you.
Perfect. Thank you so much for the presentation. I'll go to our next speaker, Dr. Gong. Dr. Gong is an associate professor in the Department of Civil and Environmental Engineering at Rutgers University. His research interests are in the field of community resilience, critical infrastructure protection, and smart cities. His recent research focuses on 2 fronts. Number 1, the convergence of geospatial big data, artificial intelligence, and infrastructure system modeling for disaster management. And 2, smart and autonomous systems for building and infrastructure condition assessment. His research has been supported by US DOT, including FHWA, the National Science Foundation, US HUD, FEMA, New Jersey DOT, among others, including industry.
So we're going to get it started, and thank you for the previous speaker to set up a stage. Wonderful talk about the infrastructure issues in the United States. So what I'm going to do actually share some of our research findings from our research project. We are about, I think, 8 months into the project. So we continue to work on it, but I want to just share with you some of the things we have accomplished so far. And of course, thank you for all the attendees to attend this presentation. And so just briefly go over my research team, like the previous speaker. So most of our work is done by this brilliant student. So I have I've been fortunate to have a group of students, dedicated students, working on different fronts of my research projects. So most of my I'm working primarily for domain our research group. Beginning would be the virtual design, construction, operation. Then we did quite a bit of infrastructure condition assessment research by fusing different data sets, and particularly on the non-contact condition assessment methods. Then really on the right side is our recent work is focusing on the smart and accessible cities, which I'm going to share a little bit of our findings into basically how to increase and actually enhance the mobility of the people with disabilities, particularly people with visual impairment and people on the ASD spectrum. So that's part of infrastructure management. We probably not only talk about the how to repair and finding the problem, fixing the infrastructure problem, but also how people use it given the current conditions. The last quarter is actually, we do quite a bit of the artificial intelligence for disaster science. I try to make sense of failures from the post-disaster reconnaissance trips, other things. But most of the work are actually done by these great students. So for this particular project, and I'm not gonna go read the text very much about it, but always we found that when we're working with the stakeholders around this region here, is the challenges for them to lack means to create a high fidelity digital environment to support the simulation of these operations, whether it's construction, maintenance, or repairing tasks. And because of the settings in the New York and New Jersey settings, it's quite complex. New York, like settings. Sometimes they say if you can make things work here, it can work everywhere. So that's what sometimes people is talking about in this way. Then we often found the traditional way of project data analysis and training methods. So it's for sure to helping the decision makers to really understand the complexity of construction tasks, other tasks. And for example, some of the larger projects on the planning here at New Jersey, New York region is some of the airports and bus terminals, which is I think reached like $1 billion projects, but quite complex in the very urban settings. How do you maintain the older one, also build the new ones, which is requires more than just a traditional way of analysis. Then of course, the project look at AR, but we actually expand a bit, also look into VR as well, because we found VR actually has a lower entrance in terms of the getting the stakeholders into that, doing the training, so which we will talk about a bit more as well. So we found that VR and AR is as immersive computing visualizing technology. We see a great amount of device come out of each year, and the Vive Pro Eye just come out, and all these things are great development. But as the technology evolves, and there's really a lack of understanding how these things mesh with the needs of these different stakeholders. So that's part of the project that we're looking into how we can help the transportation stakeholders to achieve the better understanding of these technologies, and more through demonstrations and focus groups, and how we can increase the acceptance of the technology in the life cycle management of these different systems. So our approach is at 3 fronts here. First of all, we analyze the different technologies through literature analysis and hands-on evaluation, other things, different AR devices. Then we choose a set of user cases to look at feasibility of VR and the AR technology supporting the user cases. Then based on the evaluations, we conduct additional development on top of it, doing the different modules to look at how we can integrate them to look at the project data to support interacting computing simulation in this environment. So we have been fortunate to work with a couple of local agencies here, like Port Authority, New York, New Jersey, Board of Public Utility, which manages the gas pipeline, which is underground gas pipeline, other things, utilities, and some local infrastructure companies. So we engage them as partners, more importantly, as focus groups to try these things out and to document the feedbacks, other things of it. So more graphically, and that is I would say the gist of our approach, also in a more graphic way to represent it. So on the right side, we do quite a bit of the content model development, because we found it's sometimes it's straightforward for the stakeholders to get their own facility being modeled out and simulated out, because that's going to be, they're actually going to be more acceptable to their own facility sometimes doing the simulations. So we often deploy different UAV-borne sensing and vehicle-borne sensing for that mobile lidar, and foot-on-ground sensing, including handheld 3D mapping devices in a variety of scenarios. And based on this data, reality capture of them, we build this content and models. Then we push these models and contents into virtual reality, mixed reality, and including listen to cave. And also leveraging the underlying computing platforms like GPUs and also cloud computing, Azure and AWS. And more recently, we look into the we call VDC, Virtual Data Collaboratory. It's a petabyte scalable data infrastructure actually founded by NSF at Rutgers, which provides a 10 gigabyte speed to transfer data back and forth between different universities. So we can do the collaboration, data collaboration simulations of it. Then to the bottom right, based on all these platform contents, so we often conduct demonstrations and focus groups to understand the feedbacks and pros and cons to further iteratively developing the modulars. And I know when you're doing augmented reality and use more or less, you also need a background model behind it because you want to overlay the reality scene with virtual scenes, so that give you more intelligence about it. So that's why we focus on quite a bit on content, good content and model development, and integrate good user cases. So what I'm going to, in the next 10-15 minutes, I'm going to share some of the user cases we developed for the past 8 months. Okay, and before I go in, of course, there is these are the brief summary of different VR devices. They keep popping up, and each year we see the better resolutions and different cost-wise as well, because we want low cost and more effectiveness. And also we have the look at the AR device capability-wise to try to get the best suitable device for different applications of it. I just put it over as a summary of it. But really, the example I want to share in this presentation is 3 examples. The first one is we call a bridge maintenance and repair simulation, mostly in the VR environment. The second one is also more or less in the VR environment, is critical facility simulation for different like emergency situations of it. The last one is actually the AR, but we pitch the AR in a way not actually look at the condition assessment, but more way into how we use these AR technologies, AR model development to support the mobility of the people with disabilities. So the first user case is virtual bridge for maintenance training. It's a real scale bridge, and we modeled everything detailed out from even both nuts. It's a real bridge, a cable stayed bridge passing the, I think, Mississippi River across the actual connects the Missouri and Illinois. So the modular, first of all, you bring a 1-to-1 ratio out of it in the VR environment. The come out is you can naturally involve doing different navigation about it and get a feeling about as a bridge inspector when you're getting to a top of mass what the feeling look like, and it's just a visualizing tool at the beginning of it. Then gradually we involve this tool more than into a work zone simulation module. So supposedly you want to working on the bridge, doing the bridge inspection, maintenance activities over there. What is the proper way to set up the work zones, and how do we set it up? And what for different setups, what kind of impacts over there? So in the module here, and the user actually interacts with different traffic objects, align the signs and the cones and the traffic signs over there. And the traffic is programmable. All the traffics can be programmed in terms of responding, following the traffic rules. For example, if you remove stop sign, the vehicle is going to automatically start going forward. So more or less, for people actually for the construction crew to simulate different construction zone setup with mixed traffics. And it shows you the different traffics actually can be programmable in the sense of you can mix the traffic with trailer, semis and the truck and the pedestrians, other things. And more or less, you can program the weather condition, the foggy day weather, snow night construction over there. So we actually work with a local union right now to simulate the place the traffic cones on this virtual environment. The idea would be for the highway construction workers to simulate, to put down the traffic objects in these settings, and to simulate different traffic patterns over that, and figure out the best way to set up with the work zone, the sequencing wise. The next example is actually a critical pump station which serves 3 communities over there. So that's a station as I mentioned before, we started with the reality capture to get the bin model out of it, and then starting push everything into Unity. And then in the Unity engines over there, we started simulating different accidents, fire accidents, how to put off the fire if there's fire in this facility. What do you need to do to the proper steps, 1, 2, 3, 4, to shut down what kind of systems over there, and also leaks, other things. And for example, the confined space, it's really, if you look at this one, it's just 1 story above the ground, but it's actually 3 story deep down into the ground. It connects a large sewer system into a large sewer plant. Saying it's a 3rd largest sewer plant in the United States. So it's a very confined space. And if there's hazardous gas in there, what is steps we could take to get out of there, and in what kind of time frames over there. So that's for confined space training. And if you look at it, the bottom right side, it's actually connects miles longs of the sewer lines into the main sewage plants over there. So as a navigation tool, because the nav is actually buried on the ground, no one knows what it looks like. All we have, the drawing is about it's actually the drawing date in 1910. Paper drawings. So we built out entire model and to simulate the flows in the sewer lines, and visualize different impacts, other things, and inspecting other things. So that's more in the VR environment. Then the last use case actually is more or less is around AR, augmented reality dimensions over that. The reason we're doing this because if we look at the statistics, in the United States, there are about 6.6 million people have visual impairment. And this number expected to double by 2030. And it's just naturally, also when we're aging, we lose visions. And when we lose visions, we tend to move less. When we move less, we have all kinds of side effects of cardiovascular problems and other things over there. So if you're adding things together, the low vision community, it has significant cost to the United States. And of course, we want to, ways can help this population to move around freely, more importantly, independently with any kind of guiding dogs, other things. And in second of all, if you look at the CDC's data, ASD, autism basically is fast growing developmental disorder in the United States. It's about one out of every 45 people in the United States on this ASD spectrum. And in New Jersey, I think it's among the highest in the nation, is 1 out of 42 here. So for both of these group of people, the problem is navigating the public facilities, using the public town hall, public buildings, public transportation systems like train stations, bus terminals, which is a nightmare for many of this particular group of people. And if we look at the ways how we can help them move around, we really look into the augmented reality. So one of the things that the major focus right now is look at a smartphone-based assistive technology, and we think it is more or less a fundamental augmented reality problem. So we need this situation here. If we give it a cell phone, which allows you navigating around in a facility, that requires precise localization of the users, not only location-wise, but also the orientation where they're looking at, particularly for people with visual impairment. So that's a fundamental requirement of augmented reality. You need to align the virtual scene or reality scene with virtual scenes through different localization methods, either SLAM or the method of visual SLAM. Then once you localize the user's field of view, then you can augment the reality scene with friendly navigation contents for visually impaired people, more or less all the instructions or all other sensory inputs, vibration, other things of it. So it's not a traditional way overlaying the visual content because they cannot see. It's actually different sensory inputs overlaid on this virtual scene, on this reality scene here. And also for SD users, it's more or less for graphic instructions, because some researchers found actually the graphic contents is more acceptable to SD users of it. So it's an augmented reality problem here. So in this particular project that we call Smart Accessible Transmission Hub, the idea would be how do we use a smartphone with a camera or 3D sensors like Tango? How can they use it to localize themselves in larger public transportation facilities? So we actually merged two systems. Not only look at the slant-based, the image-based alignment, we also look at beacon-based, Bluetooth beacon. The idea would be using the Bluetooth beacon to localize the users in relatively at a meter or a few feet level accuracy, location-wise. Then we use the image-based alignment to align the image view of it with a virtual model, a BIM model we call live facility model. The live facility model also integrates different surveillance cameras, knows where the foot traffic, where they are. Pretty much when driving outside, you get traffic information. For indoor, we also overlay the traffic information onto the virtual maps here. Then based on that, we come up optimized path planning for them to go to A to B over there, just using a cell phone. And because it's blind user, we not only using XYZ, but also orientation, very accurate localization of it. So this is actually a project we have been 1 year into that, more or less also funded by National Science Foundation here. So let me just show a quick video. No time is coming up. So let's say a video on the YouTube. For example, this is a service institution. We map it out using the LiDAR, laser scanners from inside out. Then we align the surveillance camera scenes with this phone cloud. Same time, the phone doing localization when people arrive at this institution here. So the app gives navigation-wise. Then the users at this critical point knows the elevator over there, it takes the image of it. We can hand the phone in front of users over there. Then the image can be aligned with behind the 3D model, the BIM model. So the node where they're facing, at the same time, they receive this augmented information from different traffic information, foot traffics over there, knowing the surrounding of it, casting to the app. Then they have optimized paths to A to B over there. So that's as a beginning step, we tried solving the augmented reality problem as a navigation problem here. Let's go back to slides. So the path forward, we in the process of comparing different training effectiveness in AR and VR and cave environment. For example, this is an environment we designed for train the autism users, actually developed by one of the collaborators, Cecilia Finley, to look at how autism users can use the traffickers to cross the streets using public transportation services and in a cave environment. And to automate the goal is looking at how we can integrate different these AR and VR and cave technology for the training. Not only just one technology, but all of them integrates what's the best way to do it. And this is my last slide. I think as part of project outcomes, we have been in discussion with local unions and local companies on future funded studies. We have some couple of NDAs with firms look at further development for the trainings, and also there are a few infrastructure companies we have been working with together to push the training module further, whether it's AR and VR or navigation applications of it.
Perfect. Thank you very much, Dr. Gong. I'll introduce our third presenters, which will include two researchers, Dr. Alexi Hain and Dr. Arash Zaghi. Dr. Hain received her doctorate from the University of Connecticut and continued at UConn as the research program manager of the Next Generation Multi-Hazard Resilient Infrastructure Laboratory. Her research is focused on using novel materials and technologies to maintain and improve bridge infrastructure. She's the co-PI in two research projects with the Connecticut DOT focused on inspecting and repairing corroded steel bridge beams. She's also the co-founder and CEO of Arash Engineering, a company that uses 3D imaging to evaluate the condition and remaining service life of steel bridges. And Dr. Hain will be the main presenter, but also with us is Dr. Arash Zaghi. He is an associate professor and the associate head for research development in the Department of Civil and Environmental Engineering at the University of Connecticut. His research interests include application of novel materials for multi-hazard mitigation, design of bridges for extreme events, innovative repair techniques for aging bridges, 3D imaging for high-precision bridge inspection, accelerated bridge construction, and large-scale structural experiments. Supported by the Connecticut DOT and FHWA, he has developed a novel repair method for steel girder ends using UHPC, ultra-high performance concrete. His work on bridge repair was selected by TRB as a high-value project in 2016. He's also the associate editor of ASCE's journal, Bridge of Engineering.
Great, thank you for that introduction, and thank you for having us. So both Arash and myself, we are co-PIs on a research project with the Connecticut Department of Transportation, and that's looking at 3D scanning technology for high-precision bridge inspection. I'm going to first touch on where the motivation for our research came from, and then move on to some of the field trials that we've done looking at the corrosion of steel beam ends, and also touching on some of our other imaging technologies looking at inspection of steel bridges. So 3D modeling and imaging is becoming much more popular in the field of civil engineering and also construction for the value that it can provide in planning, scheduling, and seeing how the different components of a project come together and really eliminating some of that risk on site. And we wanted to capitalize on this trend moving forward and see how we could use commercially available 3D scanning technology to provide high accuracy, objective data for bridge inspection. And the first area that we chose to look at was using 3D scanning technology for the assessment of corrosion damage on steel bridges. This is something that in Connecticut and a lot of Northeast states we have a big issue with. And that's something that the DOT was focused on how they could do better. So the first step was for us to find a 3D scanner that was commercially available that was suited to the accuracy demands that we had when we're talking about section loss assessment of steel beams, and also that we could use in a field that would be able to be used by inspectors. A lot of the really highly accurate scanners are often stationary, and we wanted something that we could bring with us on site. So we wanted something handheld, easily maneuverable, relatively low weight, something easy to use. We wanted someone to be able to hand someone this technology and without a large amount of training, have them be able to go out on a bridge and use it for inspection. With that, after looking at a variety of scanners, we settled on the Artec EVA, which is a structured light scanner. And how that works is the scanner projects a light pattern, and when it hits a surface, the light pattern becomes distorted. And that is then read back and collected with these two cameras, and then the software uses triangulation to then compose the 3D model. In this scanner specifically, it's under 2 pounds. The accuracy is up to 1/10 of a millimeter. It's point and shoot, and one of the best things for our application is that it requires no on-site calibration. The scanner actually comes pre-calibrated. Of course, this should be checked periodically to make sure that we don't have an issue after using it multiple times, especially out in the field. And you can do that by scanning something of a known length like a ruler. And we also modified this scanner slightly to enable easier field use. And rather than having to bring the laptop up on the cat beam with us when we're looking at these beam ends, we attached a monitor to the scanner and then had extension cables, which allowed us to leave the laptop about 40 feet away and just have much less equipment with us when we're up using this on a bridge. Before going out in the field, we practiced the scanning process in our lab environment. We were lucky enough to have salvaged beams from a bridge with corrosion damage, and we were able to go through the different steps of the scanning process. The first aspect of that was collecting the data, and that includes cleaning the beam and then scanning the surface. Cleaning the beam is one of the most important features for using this technology because it is a surface scanner. So what that means is the scanner only captures what it sees. So if we have, some pack rest, it's not able to differentiate between that being an intact portion of the beam that can carry load and something extra. So we have to make sure that we thoroughly remove all of the rust packs prior to scanning. Then we have our data processing phase, which is going through the individual scans that we collect, getting rid of extra data, aligning the individual scans, and then eventually merging that into one model. And then we move on to our data extraction, which is where we can look at the different thicknesses, compare how the corrosion profile changes along the beam. So right here, this first picture, that's the image of the beam in our lab. This is the 3D point cloud that is generated. And with this scanner, we can also overlay the texture and color in this third and final image. And what we can see here is that the 3D model really accurately represents the initial photograph of the beam. These little crosshairs that are on it, you might notice they're not on the picture of the beam. That was something that we applied in our lab trials for tracking of the scanner. And what we found is essentially we actually didn't need those. The scanner uses both the geometry and the texture and pattern to track during the scanning process. And with corrosion, we actually get a very unique color and geometry that the scanner was able to track without the need of those additional trackers. Moving on to our field trials. So far, we've gone out to 5 bridges in Connecticut. These are bridges that all have issues with corrosion damage constructed between the 50s and 60s. We're just looking currently at steel I-beam superstructures. And when we go out, we normally select 1 or 2 beam ends that have the most significant section loss or have more challenges, like they're exposed to more light, in order to really evaluate the technology. So our first field trial was just to see if we could use this scanner in the field. Would we have problems with the lighting conditions? Would an inspector feel comfortable holding this scanner on top of a ladder? So we only scanned one side of the beam. And what we found is that we were able to capture the color and the geometry of the beam. And we actually compared our measurements on site to an inspection report, which was conducted a couple months prior. And in talking to the DOT, they actually felt more comfortable going with the measurements that we could take from our model rather than the inspection report, because we could take, different heights and lengths of corrosion at multiple points and validate that. In another field trial, we were moving on to see how we could capture that full 3D model. Previously, we had just looked at the one-sided scan, making sure that the scanner worked and we could collect the data and make sure it was an accurate representation. Now we were moving on to capturing the full beam end. And what we did here was we used different alignment tools, and we also wanted to look into the cleaning process. Since we were only able to capture what the scanner can see, we wanted to be able to demonstrate how pivotal it was to thoroughly clean that surface. So we have a model of the beam end here on the right. And we found that we were able to scan one side of the beam and then scan the opposite face of the beam. And we didn't have to use a continuous scan going from one side underneath to the other. That was something we had tried in previous trials, and it was just too challenging for someone on top of a ladder to pass the scanner underneath. So by using reference objects, we were able to scan one side, move our setup, and go and scan the other face and still generate the 3D model. We see we were able to capture the severity of the corrosion on the stiffener here. And the overall data set for this was a little under 10 gigs. Following our second field trial, where we looked at scanning before and after cleaning, for our next field trial, we were actually able to scan a beam end that had been cleaned with needle scaling. Over here on this picture on the right, you see this difference in color between the gray and the light blue. That's the area that had been cleaned with needle scaling and the area that still had paint on it. We were really lucky in this regard that this was a bridge that was going to be repaired, and we were able to collect the data before it was plated. And what we found when we looked at this scan is the level of surface cleaning is very different between doing a hammer cleaning and cleaning with needle scaling. And this is kind of the perfect situation for being able to use this scanning technology. So when there's applications like beam end repairs or beam end painting where the surface is going to be thoroughly cleaned beforehand, this is a great opportunity to get that baseline data on our beams. Then we can move into what can we do with this data. And there's a lot of features that come with using the manufacturer's software. The first is just being able to take measurements between any 2 points. These measurements are in millimeters, and it's easy to use, and you can look at points along the length, and it's all manual. One of the other key features is using the section cut tool. This really allows you to make a variety of section cuts along either the length or the height of the beam and see how that corrosion, the profile of that corrosion, changes along the length. When looking at that section cut tool, we use this on one of our field scans to show the severity of the corrosion. One of the challenges that we have in typical inspections is if the inspector doesn't accurately find the area of maximum section loss, then we could be reporting a higher amount of remaining section than is actually there, which can be dangerous. When we were looking at our scan, the inspection report said that there should be 1/4 of minimum thickness of the web remaining. And when doing section cuts along the height, we actually found that there were areas that were approaching near complete section loss. Another great use for this technology is being able to take scans from different inspections every 2 years or so and see how the corrosion is changing over time. This can help us to plan for future repairs and see the rate of deterioration. If we know that certain bridges are having more severe corrosion over time, we can rehab those bridges first to make sure that we put a stop to it, perhaps before another bridge where the corrosion isn't advancing as quickly. And that's really what this scanning technology is. It's an additional tool for engineers to make more informed decisions. Moving out of things that we can do in the manufacturer's software, we've looked at using color mapping to show the severity of section loss. This is an image of the beam end without the color and texture applied. And then we can use color maps, which show the change in section from a reference plane. So we can set the reference to be the original surface of the web or the flange, and then show when the thickness drops between a certain amount. We can also show before and after cleaning to show, really make it clear to inspectors when they're going out, if they're going to use this technology, how important it is to thoroughly clean that surface. This is the model before cleaning, and this is the model after. If you look at certain locations, like right around the bottom of the web and the top of that bottom flange, there is a large amount of section that is removed during our cleaning process. And this is not using needle scaling, this is just with hammer cleaning. And then we can also use the same color mapping to show that in a different way. So we can show the overlays, and we can also use a color map to show the difference between the two surfaces before and after cleaning. So to summarize, the corrosion assessment that we've been doing with these scanners is that we've shown in the field that we're able to accurately produce 3D models of these beam ends with corrosion damage. Using this technology, it provides us a method to track deterioration over time. This doesn't need to be used in every case, but on new bridges, we can go out, get the baseline scan for the as-built condition, and then once we start seeing corrosion, be able to come back and then see the rate at which it's progressing. Having this accurate information on the corrosion damage really allows engineers and bridge owners to make more informed decisions regarding the prioritization of repairs, the remaining capacity, if something needs to be posted. And this is a project that we're working with the Connecticut Department of Transportation, and they're very excited about the future of this technology, and they've separated it out into a series of their short-term goals and their long-term goals. The short-term is to be able to perform QA/QC on the inspections and to obtain section loss information for critical bridges. And this is also for just their load rating purposes, making sure that the bridges in the state remain safe. For their long-term goals, they want to look at a variety of different applications for the scanner, using it for tracking corrosion, also looking at 3D scanning of concrete for crack mapping, using this to document bridge hits, to be able to scan historic bridges for the certain details that they're required to maintain. And they also want to come up with a criteria of when to use this technology and when to just use conventional methods. This isn't something that's going to be implemented necessarily in every inspection. It's just really for those critical times when we need more information to make an informed decision. Now I'm just going to touch on a few other applications that we're currently working on in our lab. The first is using the scan data that we're collecting and inputting that into finite element modeling. What we want to be able to do is get a more accurate evaluation of the remaining capacity of these bridge beams. And when we have the full corrosion profile, we can get a capacity estimation based on more than just the maximum section loss value. We're also looking at 3D scanning the concrete. And what's great about this is we can use the scanner on areas like stalls and then automate calculations like how much concrete do we need in order to repair this place. And so if we're on a bridge with multiple stalls, we can say for this project, you're going to need this much concrete. That can help them price it out, that can help them bid it, and really just help make that whole process more efficient. We're also looking at using photogrammetry to do 3D scanning on a larger basis. So we've actually worked with the Connecticut Department of Transportation on 2 retaining walls. And both of these retaining walls had areas of concern. For this wall particularly, there was a very small shoulder and they were noticing a bulge. And what they wanted to see is how severe was that bulge? Was there concern that this area may fail? And what we were able to do is provide a full scan of the wall and then use a color map to show them the areas of the most concern that they had to watch out for. And comparatively, they were using surveying techniques to track a few points, but now we were able to show them, the full area of concern. We're also looking at combining different data sets. We have the option to get 3D data from LiDAR, from photogrammetry, from 3D scanning. And what this really allows us to do is make digital representations of bridges or other structures and be able to have the areas of concern be modeled with a denser point cloud. And this makes our models more efficient. And this is an example of being able to do most of the bridge with photogrammetry and then just this area right here with 3D scan data. We can then take that to the next level and put this in VR and allow people to go into the model. So when they're performing their inspections, we can have one person go out in the field and collect this data, be able to bring the whole bridge back and be interpreted by a number of engineers. With that, I just wanted to thank the Federal Highway Administration and the Connecticut Department of Transportation for funding this project. Armin and Bob with the Bridge Safety and Evaluation Unit at Condot that have been working with us very closely, and the members of their research unit. And thank you so much. I'm looking forward to the Q&A session.
Yeah, that was great, interesting work. Thank you so much for the presentation. I will go directly to our last presentation, which will include two speakers, Dr. Giri Venkiteela and Dr. Dimitri Donskoy. Dr. Venkiteela is a research project manager at the New Jersey DOT Bureau of Research and is responsible for managing various research projects and the New Jersey DOT Transportation Pooled Fund Program. He's also a coordinator for the New Jersey State Transportation Innovation Council. He serves as a member of TRB's Standing Committee on Concrete Bridges, AFF 30, Adhesives and Sealers, AHD 40, and is a research coordinator for the Committee on Corrosion, AHD 45. He has published in various journal articles and provided numerous conference presentations related to infrastructure materials. He received his doctoral degree in civil engineering from the University of Louisville. Dr. Donskoy is an associate professor of civil, environmental, and ocean engineering at Stevens Institute of Technology. His research interest includes physical and nonlinear acoustics, vibration acoustic diagnostics, non-destructive testing and structural health monitoring, electroacoustic transduction, sensors and transmitters, and technological and ecological applications of sound and vibrations. His research sponsors include the Army Research Office, Office of Naval Research, Naval Research Laboratory, NOAA, NASA, DOT, and various other industrial enterprises such as Boeing, Shell, and Ford. He has published over 100 publications in his field and holds 17 U.S. and international patents.
Good afternoon. Thank you, Chris, for the introductions. On behalf of Bureau of Research Manager Amanda Gendek, I would like to first thank the Tran-SET for this wonderful opportunity. Myself and Dr. Dimitri, we are very happy to present our work through this webinar. Our topic here is detection and monitoring of fatigue damage in steel using Vibro-Acoustic modulation method. Next slide, please. The presentation here, we divided in two parts in which I'm going to cover the background of the research and the motivation of the research, and the actual research work will be presented by Dr. Dimitri. Next slide, please. We all know that steel plays a crucial role as a structural material in our infrastructure. Typically, the damages in steel structures include fatigue cracks, corrosion, sometimes joint failures, welding, bolting issues, and other issues. And most importantly, among these, fatigue cracking is the biggest issue. Currently, there are several methods that are available to detect these kind of cracks. However, most of them are extensive and sometimes laborsome also. And also they provide very localized damages. And further, the most important aspect, they don't provide a damage precursor. A damage precursor is really very helpful because they can alert the bridge owners and also help to find out the life cycle cost implications, and eventually helps to schedule a proper maintenance for the bridges. So because of these reasons, NJDOT initiated this research project, keeping in mind that we need to develop a new advanced model or advanced methodologies and tools which can efficiently identify the damages and provide damage precursors, and to quantify large areas and micro-sized defects, and to quantify the damage growth rates. So by using damage growth rates, we can able to access or predict the residual strength of the material. So that's the motivation for us for this research project. Next slide, please. These are the objectives of this project, in which we're trying to develop a methodology which can detect relatively large areas and provide a life cycle cost analysis based on the damage precursor, and also provide the test protocol where we can take this technology to the field and evaluate the structural components, and finally provide a specifications which we can use in the agency. So this is the ongoing research project. So today we are here presenting the work related to methodology only, and now Dimitri will be presenting that work. Thank you.
So first I'd like to introduce the modulation method, which was developed about 20 years ago and has evolved as a very versatile non-destructive testing and structural health monitoring method for various applications. So the idea behind method is to use two types of input signals. One is high-frequency ultrasonic signals in order of hundreds of kilohertz, and another one is low-frequency vibration. As both signals enter the test object, we may or may not interact. They interact if there is a certain type of defect present here. And this interaction manifests itself as a modulation. That's why it's called the modulation method. And typically, we're looking at the spectrum of the signal after both signals were introduced into the test object, and the modulation manifests itself as a sideband components around the carrier, so-called the carrier high-frequency signal F1. And so the severity of the defect is estimated by the ratio between the so-called the sidebands and the carrier amplitude here. And this is called also a modulation index. So, which I'll introduce a little bit later. The physical foundation behind this nonlinear interaction, which leads to modulation between the signals, is based on a so-called the contact and nonlinearity. In simplistic way, consider the defect as a crack which could be closed or open, and respectively the stress strain characteristics would be quite nonlinear. In this case, is piecewise linear. There is, of course, in reality, it's more complicated mechanism, which could be illustrated on this pictures. So where we have a contact of these two rough surfaces, where we have a lot of asperities, which some of them could be in contact, some are not. And under the application of that low frequency vibration, some of the asperities can get in contact. Furthermore, they can be pressed against each other, and this area of contact will also change, and that's lead to so-called the Hertzonian nonlinearities. So as a result, the stress-strain relationship is highly nonlinear, as shown here. It could be even hysteresis type, depending on the different type materials. So all of these nonlinearities leads to the modulation. So this slide shows a simple idea, a simple explanation for the modulation effects. Again, consider two signals entering the damage particle. And here, the low frequency vibration creates closing and opening the crack, and respectively high frequency acoustic waves propagating from this closed and open crack respectively propagates with the high or lower amplitude, leading to the amplitude modulation. Of course, this is very simplified explanation, but nevertheless, it's a good way to show the essence of this vibroacoustic modulation effect. On this slide, you see the actual measurements of from the non-defective and defective samples, and these are the spectrum. These peaks represent the carrier frequency, and these two sidebands here, and even multiple sidebands, indicates the absence or the presence of the defect. Again, the ratio of this amplitudes, sidebands, to the carrier amplitude frequency expressed in logarithmic scale, we call it modulation index and the dB scale. And if we measure the modulation index in the reference article without defects and with defective articles, the difference between, again, in dB scale, between these two MI indexes, modulation indexes, we call it damage index. Again, the higher the damage index, the greater the severity of the defect. So this idea, like I said, was introduced about 20 years ago, and since then it was studied by multiple centers, around the world. We built actually a number of field system called the N-scan. Two of them are shown here. And that was utilized for the various applications, and I give you a few examples of applications. Here is one of the applications of one of our customers was electricity difference, and where we used the N-scan system to detect crack in welded assembled pipes using nuclear power plants. And you can see here is a very good correlation between the side area of the crack and the related damage index expressed in dB. We also did apply this method for many different applications, for example, for aircraft, gun barrels, etc. This is one of the interesting application where we used this method to detect cracks in the railroad couplers in Australia. So this method requires the modification because of the nature of the test article, so we cannot really apply some shakers as we did, for example, for aircraft or the pipes. So here we modified the method and we called it impact modulation, where instead of low frequency vibration, we simply use the hammer to hit the object right here and see related modulation. So you can see that there's two superimposed signals. That's actually recorded signals. As white is a vibration picked up from the coupler, and the high frequency ultrasonic signals is modulated by this low frequency impact vibration. And so you can see again on the spectrum, we have a highly pronounced sidebands. There's more than one because the spectrum from the impact has a multiple resonance frequencies which exhibit itself in the modulation spectrum. So this was quite successful test. You can see here, the results of the test shown that the couplers with the cracks exhibits high level of modulation as compared to the reference coupler without any defects, which also here is the severity of the impact versus modulation index. So another interesting feature of the vibroacoustic modulation is ability to detect precursor of the microcracking. So here's an experiment which we conducted in collaboration with the Fracture Mechanics Lab in University of Illinois in Chicago. You can see the electronic imaging, microscope imaging of the material at the various stages of fatigue life. And you can see the changes happens as the damage evolved from the degradation 0 to development of the microcracks here, and which is very well correlated with the damage index as we introduced. So this is a very intriguing possibility to try to implement it in the real measurements, to have a damage precursor, and that was one of the goals of this project. So this is another example of the ability of the vibroacoustic modulation method to detect the precursor of the damage. This images here, that gray area here shows the damage, development of the damage illustrated with the ultrasonic microscope. And you can see as the damage progressed here, and so as the modulation index until we could start seeing a developed crack somewhere here. But we see the damage development well before the actual visual crack appears at this point. So this method, although is quite sensitive to the damage development, and these two slides illustrate the comparison between the vibroacoustic modulation method and conventional ultrasonic techniques. And next one would be the eddy current technique. So here is the screenshots from the ultrasonic, standard ultrasonic detector. The area of the damage is supposed to be here. And as you can see, this is fatigue like of the sample. The visual crack appears at this point, and this curve represents the modulation, the growth of modulation index. And we start seeing the growth using vibroacoustic modulation appears in about 80% of the fatigue life, as the only indication shown on the ultrasonic screen is somewhere here in about 90% of the life. So similarly, we see the screenshots from eddy current technique. Again, in the vibro-acoustic modulation, we start seeing it at 80% of the fatigue lives, while in eddy current, similar to the ultrasonic, detects it at about near the 90%. So to summarize, this method has a number of important advantages. So it works for various materials and complicated geometries. It's very fast. It's also interfaced with the simple data output. Basically, you can set up it in red and green light, so that would be very advantageous for automated monitoring and detection. It is a global technique, so it doesn't require sensor scanning. And it's also quantify the damage severity based on the measurements of the modulation or damage index. However, there is two major disadvantages. First, this method requires established baseline or reference, and which is fine as we use this method for monitoring, but if we just want to use it for detection, there may not, so this is not a good news here. And the second very important and very important disadvantage of the method, or the big problem with application of the method, is that structural connections may reduce the sensitivity for the detection of small defects and the precursors due to its own contact nonlinearity. So this was illustrated on this slide. So consider the structure which has many other contacts. So we have a defect like a crack, which has a contact nonlinearity, but we also have a rivets, and other connections which have their own contacts, which may lead to nonlinear interaction of these input signals. So welding, there could be some area with two parts in the contact. You can have a cheap paint, this one paint, contact between wire ropes, etc. And all of this may create a high background nonlinearity, which would therefore shadow the actual measurements of the damage. And so one of the goals of this project was, if it's possible, to still detect the damage in the presence of high structural nonlinearities. And so we have quite an interesting results here, which I will illustrate in a couple of these following slides. So here is the test samples we use in our fatigue machine, where we have a damage developed due to fatigue cycles in these areas. But in addition, just we have a small bolt connections, which also generate background nonlinearity. So this is resulting modulation index measurements. And you can see that we still see the development of the crack, but at a very late stage. So in reality, what we would like to see is what's going on here. But this is shadowed by the structural nonlinearity. Is any way to actually measure this even in the presence of this high nonlinearity? So here the hypothesis we applied is to look at the two different types of modulation. So we hypothesized that the contact nonlinearities primarily generate amplitude modulation, while the damage nonlinearities may be responsible for frequency modulation. So here is illustration, what is the frequency modulation and amplitude modulation, similar to this AM and FM radio. So here we have a constant amplitude, but the frequency is modulated. But here we have a constant frequency, but the amplitude is modulated. But if you look in the spectrum, both modulations will exhibit itself as a sidebands. So we will not be able to really recognize what kind of modulation is present here. So for this, we need to apply a different processing algorithms, which we did. So in fact, we developed a AM and FM reconstruction. I will not go into this due to the lack of time, but I will show you some results of the test. So here is, again, modulation index versus a number of fatigue cycles. That red dotted line here is the resulting modulation index based on the Fourier transform, so basically measuring from spectrum. And there's two techniques which we applied to separate the contribution of amplitude modulation and frequency modulation using Hilbert transform, and the algorithm which we developed is called IQHS, which stands for homodyne separation, in quadrature homodyne separation algorithm. So the blue line indicates the amplitude modulation, and the red lines indicate the frequency modulation obtained with the IQHS algorithms. And you can see here that indeed at the early stages, the primarily damage results in FM modulation, as the AM modulation picks up later and then dominates as the actual crack develops. So this coincides well with the unknown Hilbert transform algorithms, which can be applied in this case, but in many other scenarios which cannot be, and that's the results we develop our own in-phase and quadrature homodyne separation algorithms, which works in scenarios for non-destructive testing and structural health monitoring where HT algorithm doesn't. So here we're going back to the same curve which I showed before. Again, we have a structural nonlinearity and then damage nonlinearity developed at the same sample. And this is results of modulation index. And this, what we would expect if we would measure it without background nonlinearity. And this is actual measurements for this sample. Again, so here we have a modulation index, that black dotted dashed curve, which overshadow the actual accumulation of damage, which we see now by using separation of AM and FM modulation. Another important feature of this method is inability, or the drawback of the current method is inability to detect damage without reference. So we address this problem, and I will present the results of this research. So here what we did is the following. So we excited vibration signals with different amplitude applied to the same signal. So first we applied the low level of vibration using the same frequency, high frequency signal. And then we measure the modulation index MI1. Then we increase the amplitude of the vibration signal and measure again the resultant modulation index, which is now MI2. Now we hypothesize that the ratio of MI2 to MI1 would be proportional to the ratio of the amplitude A2 to A1, right? And then there's a coefficient K, however, which we hypothesize that if there's no damage, so the increase in MI index would be proportional to the increase in amplitude of vibration. However, the damage is a nonlinear introduction, and so that linear relationship may be not working, so the damage would indicate that this is now not a proportional relationship, so that the parameter k is actually greater than 1. And indeed, we did that experiment, which is shown here. So here we have that coefficient k as a function of fatigue life. And you can see that the coefficient k is around 1 up to 15,000 cycles, which indication that there is no modulation due to damage evolution. However, we start seeing increase in this coefficient, in large increase, especially when we do have an actual macro cracking. And this is a very good indicator that there is a damage. And this method does not require the reference data, because at any given point of life of the structure, we measure that coefficient k, and we can see if it's around 1, no damage. Is greater than none, there is damage. The greater the k, the greater the damage. So next few slides I will devote to our plan for in situ vibroacoustic measurements using bridge ambient vibration. So as you can see, one of the key parameters here is the low frequency vibration, which we introduced in the previous test, using a hammer or using a shaker. But in the bridge, especially for the monitoring of bridge, that would be probably not the practical way. So the actual ambient vibration of the bridge due to traffic or other environmental input could be used to as one of the input signal. So here's examples of the vibration of the bridge taken from the literature. And you can see as the traffic goes through the bridge, we have actually quite a significant increase in vibration. And the spectrum of vibration shown here indicates the resonance peaks, which can be used as a modulating frequency in our method. The range of the frequency actually is very similar to what we used in the laboratory. In the laboratory, we use 10 hertz, and here we have 1, 3, 4 hertz input to the low frequency vibration. In this bridge, for example, we have frequency about 10 hertz as now tests. And again, we can start seeing a large increase of the vibration amplitude due to the some traffic here. There is another example, and again, we see a different type of vibration signal from different sensors, and its spectrum, which is in the range of few hertz, which is exactly what we would like to actually use. So our idea to implement the method in the bridge, which we are working on this as we speak, is to have a two sensors, which are the ultrasonic sensor. One is transmitting and another one is receiving. Let's also have an accelerometer which could monitor the vibration of the bridge. And as the vibration of the bridge exceeds this predetermined threshold, it can trigger the high frequency signal to be recorded, emitted and recorded, together with vibration signal from the accelerometer. And thus then we will have a processing to use both of the signal to extract all of these parameters, modulation index, K index, and others, which I discussed previously. So in a summary, I'd like to emphasize that vibroacoustic modulation method reliably detects and monitors damage evolution from micro defects to macro cracks. And this method works equally well in the laboratory for a variety of materials. Metals, composites, ceramic, glass detect fatigue damage, stress corrosion cracks, delamination, and it was with some success also implemented for some test measurements. Yet the major problem with wide implementation of vibroacoustic modulation is the contact type structural elements, such as bolded connections and others, which create significant baseline nonlinearity, limiting vibroacoustic practical implementation. And this is despite of many years of and many research in different laboratories. Yet there is not that many practical implementation of the method. So, and the two major outcome of our project is that first, we've been able to separate two types of modulation, FM and AM, and using this separation, we could still measure the onset of the damage development, even in the presence of that high-level structural nonlinearities. That opens up the possibility for wide implementation of this method in practice. And the second, we also found that we can use vibroacoustic modulation without reference, and thus enabling not just monitoring, but also testing as well. And so these are two major developments so far in the laboratory, and then we are, like I said, building a prototype system to apply it in the field. So at the end, I'd like to acknowledge our sponsor, New Jersey Department of Transportation Bureau of Research, Bridge Unit, Federal Highway Administration, and our graduate students who work on this project. Now doctors Ramizani, Dr. Galshinar, we both graduated, and another graduate student is Dr. Lee. Thank you very much. This is still an ongoing project. We're studying various scenarios, conducting laboratory experiments to refine system and algorithms, and building the prototype system for field testing. I would be glad to answer any questions you have.
Great, thank you, Dimitri. So yes, this does conclude our technical presentations. Anyone does have questions, feel free to raise your hand, and I can unmute you, and you can ask your questions directly to the panelists.
Yes, I have a question on 3D scanner. So can this technology detect the damages in steel paints?
As long as it's a visible damage,
Okay.
then it can collect it. But if it's something that's going on beyond the surface and it can't be cleaned or exposed, then no.
Oh, okay. Thank you.
Mm-hmm.
Basically, the cost of this 3D scanner that can be reasonably collect, I mean, in general, field damage of a bridge or a concrete with precision enough. What is the budget or the cost, or what are the costs out there in the market in general?
I think if the terrestrial scanner right now, if we talk about equipment-wise, so the lowest costing is Leica Black 360. It's about 18K. Then Fallow is a bit more expensive. It goes to the probably 45K that range. Then of course the longer range is more expensive. Then for this really long range, 1 kilometer range above, I think that's Regal, that goes to almost 150K, 200K. If we do the mobile scanning system, the mobile scanning system is typically, think the lowest low entry is about, the survey grade either $500,000. Then the top grade would be that goes to almost $1 million each system. So, but these are just costs of technology. The system-wide and the operating cost. And at the top of my head, I think for the mobile scan, they charge anywhere between $200 to $350 per mile. And so we have been using this terrestrial scan, mobile scan on a variety of actually the Federal Highway Long-Term Bridge Performance Program. We did about 20-something bridges. Plus, I don't know if I didn't bring it up, but we do have a full-scale bridge testing facility. Right now, the first batch of specimen probably we can start testing in August. So the first are going to be in full motion
probably by mid of August, and then we already scanning all the construction process, before the pour the concrete, everything. Then during the life cycle, we basically try to punish the bridge to death in about 6 months. So shorten the city of life in 6 months. So we periodically do a lot of scan, documenting the change of the geometry, other things. If you have interest, you're more than welcome to follow up, and we can talk more about that.
And for our handheld scanning technology, the scanner that I presented on is about 18K. And
Wow.
they actually just came out with a new handheld, which doesn't require a laptop, and that's around 26K.
Mm-hmm.
Great.
Yeah, I have a question for Gong on the VR. So does this VR simulate weather conditions? That's
Yes.
the first question. And the second question is only, what about the driving skills, driving style? You cannot simulate that one, right? Or you can?
So the first question, whether yes, we can simulate night construction and simulate, snow and rain, wind, all these things in that, because it's just physics-based, simulation. We actually was I think about a month ago, we have a demo session with Port Authority, and then we talk about maybe building on some bridge. George Washington Bridge, doing simulation, some type of the scenarios when doing land closure, this type of things. So the question is, yes, we can simulate a variety of, weather situations on top of that.
Okay.
The second question is about the driver behavior. Yes. So since we did this simulation in the Unity, and the Unity is open platform, so every car can be programmed in terms of the velocity, acceleration, braking distance, and the path. So it is open-ended in toolbox. So it's basically a matter of how you want to program the car according to user behavior.
Oh, okay.
Yeah.
Thank you.
And again, thank you for the panelists, the presenters, and also for the attendees. Again, thank you so much for attending.